Hello class, this is a video tutorial on differential calculus with the exponential function part 2. In this video you're going to see how we can continue to use the same principles and applications of calculus, differential calculus, to the exponential function. In case you've forgotten, the derivative of e to the power of x is e to the power of x, or more generally, if you have e to the power of u for some function x, the derivative of this entire function is the derivative of u times the original function. So let's get straight to it. So we've been given a function f of x equals x minus e to the power of x. Let's calculate the first and second derivative. Well, this is simple enough. Here is our function, and to differentiate this, we differentiate each term. So the derivative of x is 1. The derivative of negative e to the x, well, that's just itself. And differentiating this again, the derivative of a constant, well, that's 0, so that goes away. I'm just going to leave that blank. And this, again, it's the same function itself. So now let's calculate the coordinates of any stationary points. Okay, so to find the stationary points, we need to let the the first derivative equal 0. So let's do that now. We're going to let this equal 0. We're going to solve for x. So moving the 1 over, we get negative e to the x equals negative 1. We can divide by negative 1, giving us e to the x equals 1. For those of you who are astute, we can see that if we let anything to the power of 0, so e to the power of 0 is 1. So we can say that x is equal to 1. But in case you didn't catch that, we can solve exponential functions by taking the log of both sides, so ln. This becomes, so x becomes a coefficient, so x ln of e equals ln of 1. That cancels, leaving us with x is equal to ln of 1. If you type it into your calculators, ln of 1 is 0. So that is the x value. We now need the y value for this. We're going to find that by substituting into the original function, so f of 0. This will give us, so the original function is this one. So that will be 0 minus e to the power of 0. Let 0 take away 1, equaling negative 1. So there is a stationary point at 0, negative 1. It's not asked for in the question, but we should find and determine whether that is a maximum or a minimum. And we can do that by taking the second derivative and substituting 0 into this. It's going to be negative e to the power of 0. That is negative 1, which is less than 0. That means that this is a maximum. So we can say that 0, negative 1, is a maximum. In actual fact, if you take a look, any value of x we put into here will always be negative because there is a negative as a coefficient. Hence why, well, it's always going to be a maximum, or more accurately, this function will always be concave down because the second derivative is always negative. Okay, so now this next question is, it might be new because it's very difficult, it's sometimes difficult to graph what the function may look like, because we need to know how each of the terms behaves with one another. By behave, we mean its relationship to each of the terms in the expression. And how we do that is we create a table of values, but we separate each of the terms first. So for example, I've drawn here a table of values, and often we like to use powers of 10 to see the relationship of e to the x to any other term in the function as x goes to positive infinity and negative infinity. So let's demonstrate it here. We already know that this is going to be -1, and that's going to be 0, -1, because this here is our maximum. So this is -1, this is our max. But now let's take a look at what happens as e to the x goes to positive infinity. So let's think about this. So it's going to be negative e to the power of 1. That's negative 2.7. So it's going to be 1 take away 2.7. So we're going to check our f of x value now. That's 1 minus 2. Let's actually go to 2 decimal places just to be slightly more accurate. That's negative 2.72. So 1 minus 2.72. Negative 1.72. Let's check e to the power of negative e to the power of 10. Let's do that again. As you can see, it's already gotten really large. So I'm going to write this as negative 22 ... Let's check now what happens if we make it into 100. It's actually absurdly large. So we're going to say that this goes off to negative infinity. So negative infinity. And now take a look. If we do 10 minus a really big number, that's just really negative. So we can safely say that the function goes rapidly down to negative infinity. Okay, so it's a very sharp decline. So there's a what's it called? There's a maximum here. Well, sorry, there's a maximum at this point, and it goes off to negative infinity. Let's now do the same on the negative x values. Let's take a look. Let's do negative e to the power of -1. That's negative 0.37. So -1 minus 0.37. Well, that's negative 1.37. Let's do negative e to the power of -10. Now take a look, that's negative 0.00. If we did -10 minus this answer, sorry, that's a double minus, -10 minus e to the -10. Notice how it's really just -10. That 0.0000, etc. has no significance. So this is really just -10. If we do the same thing, negative e to the -100. I know the calculator's showing 0, but really it's 0 point and lots of zeros. So really we just treat this as 0. -100 take away 0 is just -100. Now, since x is equaling the function value, that's really just y equals x. It looks a lot like a straight line, really. Oh, let's go back. So really, this is just a straight line like this, because as x gets larger and larger, e gets closer and closer to 0, meaning any number take away 0 has no significance, hence why it'll be a line. So this is what the graph will kind of look like. So let's actually do it here. So here's my 0, -1. This is essentially a straight line from what it looks like, although it should really curve as it comes close to our maximum. Let's actually fix that up a little bit. There we are. And as x goes off to positive infinity, there's a sharp decrease. So it goes down like that. And this is f of x. Now, the relationship between each of the terms will not always be the case like this, but by making a table of values and taking a small sample as x goes to infinity and as x goes to -infinity, and seeing how each of the values react to one another, you can get a general shape of what the function will look like. In any case, I hope that gave you an insight into how we can find stationary points and use those to sketch functions of the exponential function. Hope to see you in the next video. Best of luck.